In this video, I'm going to give a few illustrations of how to use the pigeonhole principle. So let's start with a simple example. We will show that in any set of n+1 integers, there are some two whose difference is a multiple of n. So let's try a quick example here. Let's say that n is equal to 5. We might have, say, -3, 1, maybe 9, 10, 17, and -5. So we only need to find two integers in this set whose difference is a multiple of n. And one quick example would be 10 and -5. Another example might be 17 and -3. Now you can check for yourself any kind of examples that you like. And if you have n+1 integers, there will be some pair of them that is whose difference is a multiple of n. And the question is how to see why this is always true. The proof will be by the pigeonhole principle. Now, we remember that in the pigeonhole principle, we need to have more pigeons than there are holes in order to conclude that there is some hole that has at least two pigeons. In this case, the natural candidate for pigeons is our n+1 integers. Therefore, we would suppose that the number of holes ought to be n. Now, in addition, we have to make sure that we choose holes that have a property relevant to the problem. In this case, we want two pigeons fitting into a single hole to mean that their difference is a multiple of n. In other words, a minus b is divisible by n. But remember that this condition is exactly the same as a congruent to b mod n. So here we have an excellent candidate for our pigeonholes. So we'll say pigeons, the n+1 integers. And the holes, we'll say, are the sets hk, which are all the integers that are congruent to k mod n for all k between 0 and n-1. Now we have exactly n holes, and whenever two integers are in the same hole, that is, both congruent to k mod n, then both of the integers are congruent. Therefore, their difference will be divisible by n. So let's just write that down. Let's name these x and y. So some two integers x and y will belong to the same h to k. So x will be congruent to y mod n. So therefore n divides x minus y, just as we desired. Now, this is a pretty simple application of the pigeonhole principle, but it actually has some quite surprising consequences. For example, we can prove, as a corollary, that every positive integer n has a multiple consisting only of the digits 7 and 0. And the proof of that is, consider the n plus 1 integers 7, 77, 777, and so on, all the way up to the number consisting of n plus 1 sevens. Then, by the previous proposition, some two of these integers, say the one with I sevens and the one with J sevens, are congruent mod n, so their difference, which is 777 dot 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 7 j minus I times, followed by I zeros, is a multiple of n. Next, we'll give an application of the pigeonhole principle to geometry. The proposition is that given any 5 points in a square of side length 1, there is some pair of those points that are at most square root of 2 over 2 apart. Now, if you're not familiar or don't remember your geometry very well, the square root of 2 over 2 may seem very mystifying. So we have to try to extract some meaning from that, try to find a hint in the problem. So let's first draw our 1 by 1 square here. Now, you may recall that by the Pythagorean theorem, the length of the hypotenuse of a right triangle, where both the lengths of the legs are 1, is the square root of 2. Therefore, we need only divide this length in half in order to get our desired square root of 2 over 2. Now, in addition, note that we have 5 points, and we need our pigeonholes to be fewer than the number of pigeons. So it would make sense to have 4 pigeonholes somehow. So naturally we would like to divide this square into 4 pieces. And the most natural way that we can see of to do this is to divide the square into quarters. Then, the length of the diagonal of each subsquare is square root of 2 over 2. And clearly, any 2 points that are in the same subsquare can be at most square root of 2 over 2 away. So, the conclusion is that our pigeons are 5 points. Our pigeonholes are the 4 subsquares. And for a pigeon to be in a hole, simply means that a point is in a subsquare. So, since there are 5 points, and 4 subsquares, the pigeonhole principle says that there are some 2 points in the same subsquare. Hence, at most, square root of 2 over 2 apart. Okay. Next, I'll present a natural generalization of the pigeonhole principle. It very simply says that if there are n holes and more than kn pigeons, then there is some hole with at least k plus 1 pigeons. And this makes perfect sense. So an example for this, we might return to our problem of people in Chicago with the same number of hairs on their head. So pigeons are the more than 2 million people in Chicago. And the holes will be the number of hairs on one's head, which is at most 200,000. Actually, for the sake of correctness, we need to say 199,999. Then, for a pigeon to be in a hole, simply means that a person has, X hairs on their head. Now, the number of holes is exactly 200,000 because we go up from 0 and go all the way up to 199,999. And there are more than 2 million Chicagoans. So by the pigeonhole principle, there are the floor of 2 million over 200,000 plus 1, that is 11 people with the same number of hairs on their head. Now, the reason that I used this floor is simply because we're saying that 200,000 is at least as big as 10 times 200,000. So in this case, our k is 10 and our n is 200,000. So since there are more than 2 million since there are more than 2 million pigeons and 200,000 holes, and 10 times 200,000 is 2 million, we know that there are at least 11 people with the same number of hairs. We'll give an application of the generalized pigeonhole principle to the following problem. Given any group of 6 people, there are some 3 that either have all met or have all never met. So here's how the solution works. Let's say that we have Alice, Bob, Charlie, Donna, Eve, and Fred. And let's suppose that Alice has met some of these and not met some others. So let's use blue for met and red for not met. So, for example, we might have that Alice has met Bob and Donna, but has not met Charlie, Eve, and Fred. So we notice that Alice has to have either met or not met, any one of these 5 people. And since there are 5 people and 2 possibilities, one of these possibilities must account for at least 3 of the other people, Bob through Fred. So in this case, our pigeons are Bob through Fred. And our holes are the people who have met Alice and the people who have not met Alice. And a pigeon in a hole simply means the person has or has not met Alice. So since there are 5 pigeons here and 2 holes, and since 2 is greater, since 5 is greater than 2 times 2, we know that one of these holes must have at least 3 pigeons in it. So let's suppose, without loss of generality, that Alice has not met at least 3 people. Now, the proof will work the same way if Alice happens to have met at least 3 people. But let's work with not met to work with the diagram. Now, there are 2 possibilities. If any pair of Charlie Eve, Charlie Fred, or Eve Fred have not met each other, for example, something like this, then those 3 people, Alice and the pair that have not met each other, form a group of 3 that have all never met. So this is one case. The second case is in which all 3 of Charlie, Eve, and Fred have met each other. In this case, this group of 3 people, Charlie, Eve, and Fred, form a group of 3 people that have all met each other. So in either case, we know that there is some set of 3 people that have either all met or have all never met. So to close this video off, I'll leave you with a challenge that is the continuation of the previous problem. For all positive integers n, if there are 1 plus n factorial over n factorial plus n factorial over n minus 1 factorial plus dot 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 plus n factorial over 1 factorial plus n factorial over 0 factorial points. And each pair of these points is connected by a line colored with one of n possible colors. Then there exists a triangle of points all of whose edges have the same color. So this problem, so first of all, a note that 0 factorial is equal to 1. And second of all, a note that this problem for n equals 2 is precisely the problem that we just solved. So if n equals 2, then we have 2 factorial over 1 plus 2 factorial over 1 plus 2 factorial over 2 factorial plus 1, which is equal to 2 plus 2 plus 1 plus 1, which is 6. And it's saying if we color the lines between each pair of points, one of two colors, in that case being have met or have not met, then there is some triangle of points all of whose edges have the same color. So that is, there's a set of three people, either all of which have met or all of which have not met. So your challenge is to prove this by induction. And try to solve this for the case n equals 3 first. And notice the pattern. In this case, the number of points will be 17. And just like in the previous problem, you'll take out 1 point and look at all the others. And by the pigeonhole principle, notice that we have at least a certain number of points within a particular category.